Alrighty, thanks for coming down, everybody. Well, I know Claudia. Alyssa, nice to meet you. All right, so today's stirring topic is responsible conduct of research. It's kind of a weird topic, and one of the reasons that it's kind of a weird topic is that this is not a formal RCR course. And so responsible conduct of research is something that's required by numerous federal funding agencies, including the NIH. And usually that involves something like 8 to 14 lectures, each of which are like 2 hours long with discussion sections and so on. And so this is the super condensed version. And so if you want to learn more about responsible conduct of research, you can buy this book, or presumably the library has a copy too, that most RCR courses use. Much of the material today is adapted or taken straight from a Columbia website that involves all this type of stuff because they phrase things appropriately. And if you are a graduate student or a postdoc or a PI, you will be required at some point to take one of these in-depth courses as well as refresher training every 5 years or so. And so this is most relevant to physicians if you're going to get a K award of some kind, or any type to become a PI on a clinical trial or some sort of basic science thing if you're going to be a physician scientist. So what does responsible conduct of research talk about? Well, it talks about a lot of things. And so we're not going to go into any of the case studies. There are case studies in the book. There are case studies on the website. There's many different websites that have some sort of RCR training. I think you can even sign up for RCR training via the city website if you want to. Probably Madison has a subscription to that course. But the main purpose of RCR is probably to talk about research misconduct. But we'll also be talking about conflicts of interest, authorship and publication, a little bit about mentoring, and then research with human and animal subjects. And I tried to make that section a little more interesting by talking about some of the research that we're doing in our lab and how that integrates with work around campus. So fundamentally, the issue with research misconduct is that the vast majority of people want to do the right thing. They want to perform carefully designed experiments that are ethically appropriate, both from a perspective of human as well as animal protection, to properly record data, to properly statistically analyze it, and to report the results in an accurate fashion. But there's a lot of concern about misconduct because there's been many cases of misconduct over time, and these get a lot of press attention, even if the overall rate of misconduct is fairly low. So the federal government defines research misconduct as fabrication, falsification, or plagiarism. And this can be involved both in the performing of research, the proposal of research, or reviewing research. And the definitions are here. So fabrication is simply making up data or results or recording or reporting them, while falsification is manipulating either research materials, equipment, processes, or changing or omitting data or results such that the research is not appropriately reflected in the literature. And so this can include things like inappropriately omitting experiments that have opposite results from the ones that are being reported. And plagiarism is the appropriation of another person's ideas, processes, results, words without giving appropriate credit. You'll note that in today's presentation, I gave credit for a lot of this material to the book and the website. So that is our appropriate credit here. And research misconduct does not include either honest error or differences of opinion. And there are lots of times that there are differences of opinion that are very strong and heated, and this can include differences of opinion about the appropriate interpretation of research data. But that does not count as research misconduct, nor does the federal government consider self-plagiarism, which we'll talk about a little later, to be research misconduct, even though some people feel that is inappropriate. And so the Columbia website gave a number of examples of famous historical examples of research misconduct. I was not aware that Isaac Newton apparently manipulated his data to make his calculations better. I guess in the end, it all worked out for him, but obviously that's not appropriate. It's sort of well appreciated in biological sciences that Mendel's idea of Mendelian genetics is based on falsified data. And anyone who has bred mice, for instance, is well aware that you never, ever, ever get Mendelian ratios, basically anything. You get close to Mendelian ratios, but it's never perfect. Apparently, when they were figuring out the charge of the electrons, some of the data points were outliers and eliminated, and one can argue that should have been reported appropriately. But standards change over time as well, and so nowadays we're much more alert to that. And apparently Pasteur substituted someone else's reagents and claimed them as his own. So obviously that is not acceptable either. There's many more recent cases. For instance, the most relevant historical one is the David Baltimore case, which dragged on for something like 10 years in the 1980s and maybe early 90s, where there was a big brouhaha that resulted in the imposition of many of the federal requirements surrounding research misconduct, even though in the end it was decided that no research misconduct had occurred, simply sloppy research. So in terms of reporting misconduct, the National Academy of Sciences says that we are all obliged to report research misconduct when we observe it. The important thing to note here is that misconduct is almost always investigated first by the institution. It's very rare that the Office of Research Integrity, which is the federal agency devoted to research misconduct, directly examines anything. Usually the institution, UW-Madison, or potentially the VA hospital are the institutions here that investigate misconduct. And you can just Google the website if you want all the information about Dr. Fox and how you can contact him and all the various procedures and regulations at Madison related to research misconduct. It's important to note that there are whistleblowing regulations that protect people both at the state level and the federal level for reporting allegations of misconduct. But the Columbia website wanted to highlight this fact, which is that ORA says the Office of Research Integrity found that despite this, about 2/3 of all people who report research misconduct experience some negative consequence of some type. And I think that that's not unexpected. You can imagine basically the same thing happens in any occupational health setting as well, or labor setting. Some general guidelines for those who are reporting allegations of misconduct. One of the first and most important things is documentation. When making an allegation of misconduct, documentation of who did what and when they did it provides the best opportunity for someone who is impartial to investigate the situation. It's also noted, though, that one should not necessarily violate other regulations in the process of making this documentation. So, for instance, in a neighboring lab during my postdoc, there was a postdoc, or a graduate student rather, who felt that a postdoc was contaminating their solutions during the night and sabotaging their experiments for about 1.5 years. And so they set up a camera and recorded their bench for a long period of time. And indeed, they found that this is what was happening. So the postdoc in question obviously got fired and had other sorts of situations, but the graduate student was sanctioned as well for making unauthorized recordings in the laboratory. Rules of procedures. Misconduct is investigated by the institution, as I mentioned. Overall, many times there's concerns about potential research misconduct by people who have little experience in research. And so a general guideline is that if you expect that there is research misconduct, you should discuss it with others first before making a formal allegation in terms of other trusted mentors or other PIs. Some allegations of research misconduct might be more appropriately thought of as something that's handled in a dispute or conflict resolution, depending on exactly what's going on. And motivation of a whistleblower is sometimes questioned. And so, it's very difficult to understand what's going on in someone else's mind. And so generally, the key is that there be this clear distinction between facts and speculation and motives. And from a research misconduct investigation standpoint, asking questions is more about, is something appropriate, is perhaps a better way than trying to draw conclusions. Okay, moving on, conflict of interest. So conflict of interest is something that's very important both in the basic science perspective as well as from the perspective of physicians. Obviously, there's a lot of concern about physicians taking various gifts or trips or even pens nowadays from pharmaceutical company representatives. And so basically the problem with conflict of interest is that we have this idea that we are unbiased investigators of truth, and so in order to get to that truth, we need to be objective. And so conflicts of interest, which inevitably exist in one form or another, threaten our objectivity. And so when we think about what a conflict of interest is, a conflict of interest is any situation in which either financial or other personal considerations have the potential to compromise our objectivity. It doesn't mean that it is compromising our objectivity. In fact, many people, when they are aware of bias, tend to overcompensate in the other direction. But a disinterested observer might still suspect that there is a conflict of interest there, and it's the appearance that is the real problem. So an apparent conflict of interest is one in which a reasonable person would think that the professional's judgment is likely to be compromised. You can imagine a wide variety of potential cases where that might be the case. A potential conflict of interest involves a situation that may develop into an actual conflict of interest, but hasn't yet. And a conflict of interest exists whether or not the decisions are affected. It only matters if there's a potential for those decisions to be affected. A conflict of interest is not considered misconduct in research because, as we mentioned, the definition is only related to fabrication, falsification, and plagiarism. But obviously, it can still affect how research is reported and discussed. So there's two major categories. So intangible, which involve academic activities and scholarship, and tangible, which essentially involve money or money equivalents. Most of the intangible conflict of interest relate to the concept of peer review. So what is peer review? So peer review is a generally blinded process that's conducted both by academic journals as well as by granting agencies and many other institutions as well. And so if we submit a manuscript or we submit a grant, it's peer reviewed generally anonymously by other people who have interest and expertise in that area. And so we recently submitted a manuscript that's going to come out tomorrow in Nature Communications, and it involves a drug from a company, and so we'll talk a little bit about that. But that manuscript went out for review, and 3 individuals, perhaps 4, provided comments about the manuscript, which led us to make revisions both in the text and to perform additional experiments. And after a couple rounds of that, the editors in the journal decided that we had done enough, and most of the reviewers were satisfied with our revised manuscript, saying that our data appropriately reflected the conclusions that we drew and was valuable to add to the scientific literature, and so that will come out tomorrow. Same thing is true, generally speaking, with grants. If we submit a grant to the NIH or other funding agencies, it goes to a peer review panel. Depending on the exact agency, exactly how blinded it is sometimes not clear, but basically there's usually a panel of about 20 to 30 people, and you know that all of them voted on your application, but basically only 3 of them read it. And so, well, you look skeptical. So an R1 application is about 100 pages, and obviously people are overall, and the research plan is about 12 pages, pretty thick. It takes probably a minimum of about a couple hours to read one of these things. And so people generally score about 9 applications, that's about 18 hours. Then they go and discuss. And each of the applications in an NIH panel is discussed for about 15 minutes. The first reviewer provides the most in-depth review. and gives a score. The second reviewer gives an additional in-depth review. And the third reviewer basically gives a very short review in most cases and gives their score as well. And so if the scores are all basically the same, everybody on the panel is going to vote to give it that score. It's discussed freely for about 10 to 15 minutes. That's generally the case. And so if other people feel very strongly about it one way or the other, they will weigh in, and sometimes that definitely happens, and sometimes nobody else has anything particular to say about it. Pretty much everyone on the panel will read the specific aims page, but not otherwise read the grants except for the ones that they're assigned. And so this is great, but there are a lot of issues with peer review. One of which is it takes a really long time. But in terms of what's relevant today, reviewer bias or conflict of interest is always a potential issue. And so for our paper, we excluded both my old postdoctoral mentor, who founded a company that competed with the company that provided the drug to us. We excluded everyone else associated with all the companies we know about pursuing similar drugs, which is quite a big bit of people. And so, of course, a lot of those people have appropriate expertise to critique the manuscript as well. And so you can imagine that there's almost certainly some people involved who have some sort of bias, solely from a financial perspective, but potentially from the scientific one as well. In terms of other conflicts of interest, you could imagine that if you read a manuscript and you have a manuscript that's on the same topic, you might be inclined to rate that manuscript not so well if you want to delay it. And certainly this is something that has happened in the past, that people give bad reviews or slow to review manuscripts because they want to get their own paper out first. Obviously, this is not appropriate conduct. Peer review might not allow controversial, innovative ideas. And so that's definitely true if you're proposing something that breaks existing paradigms. You're going to have a hard time publishing it, and you're going to have a hard time getting money on it unless you have really, really compelling data. Peer review does not prevent papers from getting published. People just resubmit their papers, hopefully revising them to deal with some errors. But, at some level, sometimes you have things that are done and are not that interesting and you need to get out. And so eventually you're going to get them out in a journal. And they certainly don't catch all errors. And there's all sorts of things that come out. The one that caught my attention most recently is one that claims that global warming is due to the motion of the sun. Apparently the sun moves. The sun is not stationary relative to the rest of the solar system because Jupiter pulls it out of position, which is apparently true, but it's not relevant to the fact that it's not relevant to climate on Earth in any particular. And there's a lot of people who are pushing for peer review to be open, for peer review comments and manuscripts to be published, for names to be published. I personally feel that's a terrible idea, mainly due to the fact that for the most part, you can imagine that particularly for junior investigators, if you're peer reviewing a manuscript and you are peer reviewing a senior person's manuscript and they're deciding on your grants, then there's potential either way, either positive or negative, for that to affect grant decisions. So into other intangible, this basically covers most of what I just said. But of course, there's also personal friendship as a potential issue. If you're friends with someone, probably you're more likely to accept their manuscript, and so that could be a negative problem. And you conversely, if you are really on bad terms with someone, maybe you should exclude yourself from being a reviewer on their manuscripts or their grants. Certainly, during grant review, you're not allowed to review grants for the NIH, for instance, if you've collaborated with someone in the past 3 years, if they've been a postdoc mentor in the last 3 years, if you are currently working on a grant or project with them, or if they're at your institution. So I can't review grants for anyone at UW-Madison. Some other interesting types of conflict of commitment conflicts include conflict of effort. And so this is kind of an interesting one. So this is when the extent of time spent on a secondary activity competes with the time that you're supposed to be doing teaching, research, or service. Many universities have policies allowing about 20% of faculty time to be spent on outside activity. I'm not aware of what the exact details of UW-Madison's policies are in that regard. It hasn't come out for me. But the weird thing about effort is that effort is from total time, and it's not based on 40 hours a week or 50 hours a week if you're at the VA hospital is supposed to be your standard calendar. So you might think that if you're working 40 hours a week for UW-Madison and then you want to work 40 hours a week for a company, that's fine because it comes on top of your UW-Madison time. But in terms of effort calculations, it's calculated then that 50% of your effort is being devoted to an outside source, and that is not okay. So that's kind of an interesting thing, and effort calculation is very, very interesting. Clinical research. So you can imagine that all sorts of potential bias exist in clinical research, particularly in the selection or retention of research participants, adverse event reporting, collection, statistical analysis, and reporting of data. And so when we think about how a clinical trial is designed, you'll note that most phase 3 trials are large, multi-center, include a center that collects all of the data and information about adverse events as well as positive events in a completely blinded fashion where the people who are actually conducting the research aren't able to influence it. And it's all predetermined about what type of statistical analysis will be done, what outpoints will be examined, and as well as when that will occur, and what type of adverse events might lead to premature termination of a trial. And all of that pre-selection of what things are being done is done to try and eliminate bias, because you might start looking for secondary outcomes that are not really relevant if your primary outcome fails, whereas fundamentally, if you're looking for a drug and it's supposed to treat a specific disease and it's supposed to do something, a particular something to their blood glucose levels or so on, clearly, setting that in advance of the trial is probably the best way to do it. And it's in the clinical setting that you have the worst possible outcomes from damaging overall research and reducing the public's trust in research, because you might be harming people. So federal conflict of interest regulations, aside from ones related to grant review panels, are primarily focused on financial conflicts. And the key components here are that the institution has the responsibility to analyze and assess these conflicts, but basically they all work out the same way, which is that the institution has a system for disclosing significant financial interest. And then the institution must report to federal funders if a significant financial interest exists that could affect the research. The VA requires additional forms to be filed with grant applications, but that's a separate issue. Significant financial interest is defined as basically anything of monetary value or potential monetary value, as well as intellectual property rights. It does not include salaries, royalties, or other things that come from UW-Madison, UW-MF, the VA, etc. It does include income from seminar or lectures or teaching, but not if they're done by public or nonprofit entities. And income from service on advisory panels or review panels for public or nonprofit entities, but for profit entities would be count. And significant is basically defined as ownership in stock options, or other ownership interests that exceed $10,000 in value, excluding mutual funds that are not directed by the individual, or more than 5% ownership in a company. And interestingly, it includes equity of the investigator's spouse and dependent children as well. And that's actually quite interesting. And so, for instance, my wife works as a medical writer for DaVita Clinical Research, and no journal's policy is consistent on this, but JCI requires me to report that as a potential conflict of interest, even if my work has nothing to do with kidney dialysis. So authorship. Authorship is something that often comes up in the lab. Who is an author? And so there are established guidelines on who should be an author on publications. Basically, the idea is that the person made substantial contributions to conception or design, acquisition of data or analysis, or interpretation of data, drafting the article and revising it critically, and approve the final version to be published. And the authors need to meet all three conditions. And generally, it's appreciated that acquisition of funding, collection of data, or general supervision of the research group alone does not justify authorship. and that each author should participate sufficiently in work to take public responsibility for at least a portion of the content. And finally, the order of authorship on the bylaw should be a joint decision of the co-authors. And other people who contributed should go in the acknowledgement section. So, I have problems with these guidelines. And overall, the major issue is that many members of the scientific community are unaware of the guidelines, and many scientists do not subscribe to them. And I think the interesting question to talk about is why. And so, first off, the one big reason is this idea is that everybody on the paper should be able to take responsibility for everything in the paper. Well, for instance, we're working in papers in my lab right now where we're looking at the epidemiological analysis of data as it relates to consumption of amino acids and the statistical analysis of that. I have no understanding of that. That's why I went and talked to an epidemiologist. She has a PhD, she directs the epidemiology program, she's responsible for understanding how to do all the statistical analysis and coming out with appropriate data. I have no expertise in that. I've also been an author on a paper where people have used advanced biochemistry data or structural data and analysis of like X-ray crystallography. I have no expertise in that. I'm a physiologist. I know some molecular mechanisms too, but all these things are outside my expertise. And so it's a complete relic of a previous age that people could take responsibility for all of the contents of a paper. You can take responsibility for part of a paper, but taking responsibility for all of it is outdated. There's also one problem that's pretty serious. The idea here that acquisition or collection of data alone is not sufficient for authorship. And I think that's also a relic of a previous age. And that's for two major reasons, one of which is fundamentally being able to collect data in an appropriate fashion is, in my opinion of many others, an intellectual contribution. Because fundamentally, you are using your brain and your skills to figure out how to collect data from that animal or that cell or whatever. From a practical standpoint as well, if you do not include technicians or undergraduate students on your papers and manuscripts, they're not going to be able to get into graduate school or medical school because nowadays that's something that's just required for scientific advancement. And so if they're using their brains, and one of the things that we want to do in my laboratory at least, and I think many others, is not only collect the data, but analyze it. So they meet multiple contributions and actually produce a graph that will go in the paper. But there are many labs run by PIs who are trained in an older generation where there are technicians who generate all the data in the paper and then they're not included as authors. And I think that's inappropriate. And so some journals have turned away from the idea of an author, and as well as they simply designate someone who's willing to take responsibility for the content of the paper. And many journals, such as JAMA, have a form or something at the end where people specify what their contribution was to the paper, who collected data, who provided funding, who did what. And so I think that's becoming much more of an accepted way of dealing with these facts. And you could simply list at the end of the paper, well, so-and-so didn't do anything but get money. On the other hand, they got $1 million to run a clinical trial. That's a pretty big contribution to the overall paper if that's, if it's reporting a clinical trial. So authorship problems that occur in the lab, first of all, inadequate credit. Obviously, many people who have contributed might feel slighted if their data was used, but they're not included as an author. But there's very commonly authorship fights between people in laboratories, not so much in my experience here, but some laboratories, for instance, one in particular I'm familiar with, only has 3 research projects. And so they're focused on 3 research projects, and they have about 50 people, and they have to work on those 3 projects. And so at the end of the day, there's a big fight at the end on who gets to be first author and so on all their publications. Plagiarism. So obviously plagiarism is a problem. With the introduction of software to check for plagiarism, this has become somewhat less of a problem, or at least it's being caught very frequently. Self-plagiarism is interesting. As I mentioned, it's not considered research misconduct by ORI, but self-plagiarism is considered bad by various journals. But there's sort of an issue here, and it particularly relates to method sections of papers, which is if you fully described a method and you've done the same method in multiple papers, why wouldn't you have the same text describing it in multiple papers? you could always reference the previous paper. But that's also considered bad because then you no longer have the full methods necessary to perform the experiments within a paper. And so in method sections particularly, it's, I think, generally accepted that at least some degree of this quote-unquote self-plagiarism, reusing your own words that you wrote, if the methods are the same, then they should be described in the same full, complete way. And the last is allowing sponsors to control publication. And so overall, it's now considered very inappropriate for sponsors to be able to control publication. If sponsors are donating money to UW-Madison to perform research, the agreements that are signed usually specify that the sponsor has a limited amount of time to pre-review the publication, usually about 60 and 90 days, but they are not allowed to control the decisions to publish. And this arises from a variety of cases in the past where people have been funding investigation, or companies have funded investigations of their drugs. It turns out that the drug either doesn't do anything or hurts people, and then obviously they don't want to publish that. And so this is one reason that this is considered inappropriate now. That said, one of the things that's in, when you do research with a company, there's always the potential, right, for the company to control publication in less serious ways, and that needs to be, thought out and well considered from an ethics standpoint. One is if they pay you to conduct a study, and that study suggests that there should be some follow-up studies that would make the paper that you're going to hope to publish much stronger. Well, who's going to pay for that? Are they going to pay for that? And if they're going to pay for that, does that mean that they're effectively controlling your publication of the original results? There might also be other issues, like the fact that many companies might provide drugs without providing the structures. And generally speaking, in order to publish in a good scientific journal, you need to be able to publish the structure of a drug. And so there are different ways that sponsors can control publication, even if it's not formally. And so people who are conducting research with companies need to consider that very carefully. And finally, we'll just talk briefly about mentorship. So mentorship is very important, and so you may be aware that mentor comes from the Odyssey, where a mentor was someone who trained and advised Odysseus' son. And overall, a mentor is someone who has experiences with challenges that trainees face. Very often is someone in a supervisory position, but it doesn't have to be. And so the National Academy of Sciences define this as being an advisor, teacher, role model, and friend, potentially advocate as well. But of course, there's a potential for abuse in mentoring relationships, particularly ones where the mentor is in a position of authority over the trainee. And so obviously there needs to be good consideration on both the mentor and the mentee's part in trying to keep that a healthy relationship. And obviously people can seek advice from other mentors if things seem to be imbalanced or there seem to be problems in the relationship. One of the things that is most relevant to graduate students, and I think that this is an interesting issue at Madison, and I don't know why it's not been addressed specifically, is that at some other institutions, the thesis committee that makes the decision about whether someone should be allowed to defend their thesis does not include the PI, whereas in Madison it always does. And so that means that there's advantages and disadvantages to this. But I think overall that there's an advantage to removing the ability of a student to graduate decision from the PI, because that way the PI is not able to necessarily retain someone in the lab inappropriately just because they're very productive. So the next portion of today's talk, I'm going to talk about vertebrate animals and then human research, and then the ethics of that, as well as provide you with some examples. So we really need animals for research, and we need animals for research for a variety of reasons. First of all, animals serve as really good models, and many of the disease processes that people study can only be studied in intact animals. So my laboratory studies aging. Aging is something that happens to a cell, but it's not really that relevant to what happens to a human or companion animals. And there's many other complex physiological processes, for instance, diabetes, which my lab also works on, where you have multiple organs all working together, all communicating with each other. And it can only be studied so far in the whole animal. There's no way to model that in a computer or a dish. And animal models overall are used both to understand how diseases affect tissues, develop and test treatments, as well as train future scientists and physicians, although certainly to a degree that's being replaced by very complex models. There are many similarities between animals and people, and so animals are used to provide an index of safety. It's mandated that animal studies precede and support human studies. This turns out apparently not to always be true. There's a recent book that talks about the development of a cure for or treatment for AIDS, some of the first protease inhibitors, and I think the book is called How to Survive a Plague. And so in it, there's a description of Merck's development of one of these protease inhibitors, and apparently they called the VP of research called up the head of production and told them to establish a production line, which cost millions of dollars for a medication. And they were like, but you haven't trialed it in animals. And apparently he was informed that there was a big chimp experiment. And apparently a big chimp refers to a human who injected something into themselves, and they were okay. But, in the context of AIDS, where there was both a plague and a lack of animal models, maybe that's not always possible. But for the most part, generally, before a compound of any kind goes into a human, it goes into at least 2 mammal species, usually mice or rats, sometimes both mice and rats, and then something larger, ideally a pig or a sheep or a dog, depending on what type of you're looking at. And the Declaration of Helsinki also mandates that this type of animal research, wherever possible at least, should be supported by preceding animal research. I don't know if you're familiar with the story, for that matter, of the development of the idea that ulcers could be treated with antibiotics. So Presser was a pathologist who saw that in all of these ulcer studies from humans, they were colonized with bacteria in almost every case. And so he was very focused on the idea that bacteria could explain, and H. pylori in particular, could explain the development of most ulcers. But no one would believe him. And so the story, at least, is that there was a big conference where no one would believe him. And so he drank a liter of H. pylori on stage. And then very quickly thereafter developed ulcers that were then treated with antibiotics. So anyway, I just like that story because, it's sort of like such a clever story of someone who truly believed in their research, even though they couldn't get anyone else to do it. Obviously, he probably also suffered with problems with peer review due to the fact that he was breaking the existing paradigm that ulcers were stress-related. So, tons and tons of medical advances are based on studies that were done on animals, basically every drug. But animals can't give informed consent, so we need to make decisions for them. And an important note that researchers should realize is that animals whose needs are met and are healthy and happy generally are the ones that are best for producing reliable quality data. And so animal welfare and the accountability for it are the driving forces behind regulations and oversight, particularly public institutions where there's a lot of information available to the public about what happens to animals. So we follow the 3 R's, and the 3 R's are replacement, where we try and use non-animal alternatives or lower orders of species wherever possible. Reduction, where we try to use the least number of animals necessary for statistically valid results. Well-powered studies, where we don't have to repeat things because we didn't use enough animals. Try and eliminate duplication of research. And then we try refinement as well, particularly to minimize pain and distress. So different ways of handling the animals, different medications or analgesics or anesthesia to reduce or eliminate their distress. And so the reduction part is something that I focus on very heavily. Claudia is familiar with the fact that we talked about it at a lab meeting. If we could use the same control group for multiple experiments at the same time, while keeping everything logistically feasible, that's a better way of approaching things because not only does it save money, it lowers the number of animals, it lowers the amount of animals who need to be used for the research. Many different agencies oversee animal use. They have many different hundreds or thousands of pages of guidelines. Some that you might be familiar with are ALAC and OLA, as well as the guide for the care and use of laboratory animals, which is often cited in animal protocols. And self-regulation is the order of the day. So we have an institutional animal care and use committee. There's actually 5 at UW-Madison. I think that includes the one at the VA that I'm on. And we have various protocols at SOPs dealing with all of our animal use. And also through FOIA or Wisconsin Open Record Law, and also open record laws that relate to the VA, the public could get a very good idea of what type of animal research is happening. There's a lot of training, so everyone has to do an animal health risk questionnaire because some people develop allergies to different animals. I'm sure there are other reasons too, but that's the primary one. As well as tons of different animal training available from RARC, which is the major animal trainers on campus. But the key is that all activities with vertebrate animals must be approved by the IACUC prior to initiating them. And the IACUC reviews or approves or denies protocols and amendments and renewals for all of these types of things that we want to do with animals. It's an agreement between the PI and the IACUC, and thus a deviation from this is essentially a violation of this contractual agreement and a protocol violation. And various other things that can happen, such as animals unexpectedly dying, could also be protocol violations or at least a reportable event. And UW-Madison and the VA are obliged to report violations to various different agencies, depending on exactly what species is involved, after an IACUC investigation and remediation. So overall, the other ideas, as I mentioned, so clean animals equals clean data. To keep pathogens away unless you're studying a pathogen. Happy animals equal clean data, so things like noise, heat or cold, or odor could all stress out animals. And keep personnel safe. And one of the easiest sources of violating various things that also doing harm is treating animals with chemical or biological agents that are then passed along either to the people manipulating the animals or those changing their cages. So I'll tell you a brief story about some of the work we do in our lab. So we're really interested in understanding how diet affects health in both animals and humans. And so when we think about a diet, there's 3 major sources of calories in a diet: protein, fat, carbohydrate. And of course, lots of people say fat is bad. More recently, it's been said that we should all be on keto diets where we limit carbohydrates. But actually, there's a lot of data in mice suggesting that low-protein diets can extend mouse lifespan. And there's human data to support this idea as well. So low-protein diets are associated with decreased rates of cancer and mortality in humans. Diabetes risk actually doubles with increased consumption of proteins. This was a large prospective cohort study trial where the endpoints were pre-registered, and then 40,000 people were followed for 10 years. And the people in the highest quartile protein consumption had twice the diabetes risk of those in the lowest quartile. And smaller studies have shown that high-protein diets associated with things like increased cardiovascular mortality, as well as smaller brain size, although no one quite understands what that means. So with Luigi Fontana's laboratory at Washington University in St. Louis at the time, he has since moved to Sydney, we examined metabolic outcomes during a human clinical trial of protein restriction. And so in this study, people were fed either a low-protein diet in the hospital cafeteria. They received 7 to 9% of their calories in the form of protein, or they ate at home and just wrote down what they ate. And they ate about 17% of their calories from protein, which is fairly standard for Americans. And the thing that really jumped out at us was that there's decreases in weight, fat mass, and blood glucose levels. Basically, the people lost about 1.5 pounds a week for 6 weeks, and they had about a 5% decrease in their fasting blood glucose levels. And this was not due to calorie restriction. So the people in the protein-restricted diet actually ate more. This is well appreciated both humans and rodents because dietary protein is satiating. And so we wanted to drill down and understand what was really mediating effects, looking at the building blocks of protein, which are the amino acids. And particularly, we focused on the branched-chain amino acids, leucine, isoleucine, and valine, most familiar to many of us due to the fact that muscle builders or athletes take a lot of branched-chain amino acids to build skeletal muscle. But interestingly, high levels of branched-chain amino acids in the blood are well correlated with diabetes, both in humans and in animals. And in our dietary protein-restricted individuals, we saw a decrease in branched-chain amino acid levels, but not other amino acids. So we thought that these would be good ones to look at. And I'm just going to show you one of the most dramatic experiments. In this set of experiment, we took black 6 mice, a standard inbred mouse strain, and made them fat by feeding them a high-fat diet for 12 weeks. We had some chow control mice, and then we switched them to a series of amino acid-defined diets that let us manipulate very specifically the amino acid composition of a diet and nothing else. So overall, the number of calories from dietary protein in our high BCA, low BCA diets are identical. Our low AA diet, we had to supplement with carbohydrates. So that's a high carbohydrate, low protein diet. And primarily, we were looking at weight. And so what we found was that here's our obese mice, here's our lean mice. When we supplement with extra branched-chain amino acids, nothing happens to weight. But if we restrict dietary protein or restrict branched-chain amino acids, they lose a lot of weight very quickly. And so this was covered on our animal protocol. One of the things that is usually a poor sign of health in mice is loss of weight. And so we want to make sure that that was in accordance with our protocol. And so we clarified in our protocol that weight loss could be expected, and the idea was that they would achieve a steady weight in the study. And indeed, they do. And you can see that basically they lose about 25% of their body weight in a very short period of time, about 3 weeks. So this could potentially be a really interesting intervention in humans. Particularly for obesity interventions, there's a big concern about losing lean mass, particularly if you lose a lot of weight rapidly, it can damage your heart. But what we see here is that we actually see almost an exclusive loss of adipose tissue in these animals and very little change in lean mass when we restrict branched-chain amino acids. And other correlates include fat blood glucose levels and insulin levels, insulin resistance as calculated by HOBA2IR, which is something used for ubiquitical trials, all suggest that the more branched-chain amino acids you consume, the worse your fasting blood glucose is, the higher your fasting insulin is, the greater insulin resistance you have. Whereas conversely, if you decrease dietary levels of branched-chain amino acids, you get lower fasting blood glucose levels, lower fasting insulin levels, and improved insulin sensitivity. We also performed a glucose tolerance test, which is very similar to those types of tests that are often performed in humans to clarify whether someone has diabetes. Basically, we administer glucose to a fasting animal and then see what happens to their blood glucose levels over the next 2 hours. The higher area of the curve indicates glucose intolerance, just as it would in a human, whereas if we lower the fasting blood glucose level, we improve glucose tolerance significantly, indicating less diabetes, if you will. Better blood glucose control. So what we concluded was that decreasing dietary protein or branched-chain amino acids improves metabolic health, and that decreasing branched-chain amino acids or all protein restores metabolic health to diet-induced obese mice. And so this led us to the question of whether or not we could translate these results to humans and either intervene in the diet by reducing dietary branched-chain amino acid, or potentially someday coming up with a compound that does the same thing. And so we wanted to conduct a clinical trial. And so one of the med students in our lab, Elizabeth Williams, made this flyer several years ago. And we decided to call it SOAR, Stop Obesity and Diabetes by Amino Acid Reduction. You'll note, interestingly, that the title of the study here is the metabolic response to reduced branched-chain amino acids in humans. That's due to the fact that the study sponsor wanted to make clear that we're really studying the metabolic response here. Rather than seeking this as a trial that's going to definitely serve as an intervention. And that's true because, for instance, we have no idea whether decreasing dietary branched-chain amino acids in humans might make their health worse. And so that's something that we need to consider. We used BCAD2, which was provided by Mead Johnson, which makes it. BCAD2 is a branched-chain amino acid-free medical powder used for treatment of maple syrup urine disease, where people are unable to metabolize the branched-chain amino acids, and if they eat too many, they suffer from neurological problems and others. And Mead Johnson has no control over anything. They just give us the powder, and that's it. And so they have a contracted place with UW specifying that, yeah, they agree to give us this many kilograms of powder. They hope we publish the results someday. In terms of resources and access, A lot of resources and access for our trial are provided by ICTR, which is an NIH-funded center here, the Institute for Clinical and Translational Research. And all of our studies were performed at the Clinical Research Unit, which is free for investigator-initiated trials and provides both nursing support, dietitians, and other resources for the trial. And so a lot of things that you could do if you're interested in clinical trials is to visit the ICTR website and sort of look at some of the things that they have. There's also, of course, the need for a human subject protocol, which goes through the Health Sciences IRB, Institutional Review Board. Much like IACUCs, we believe here that having more is better. So there's 3 different IRBs, plus 1 at the VA, so 4 IRBs and 5 IACUCs. When we think about what's required for training, for human subject research, there's a lot of things required. So on that Health Services IRB website, there's training. Everyone needs HIPAA training, but there's also human subjects protection training, good clinical practice training, and then fighting with the billing system and the clinical trial. The clinical research unit uses Encore, which is from, I believe, the Carbone Cancer Center here. But in any event, it's overall quite difficult to use. I think Encore is like 6 hours of training, maybe more, and even after that point, you're not very good with it. Everyone who does human subject research needs an IRB-approved protocol or an IRB-approved exemption from having a protocol. A protocol goes through multiple stages, which includes scientific review to examine whether or not the outcomes are appropriately defined, whether the statistics indicate that there's sufficient power. We don't want to do a study and discover that later that we didn't enroll enough individuals. We don't want to enroll so many individuals that it's ridiculous. And also that there's appropriate scientific justification. And so scientific review happens for anything that's not already been funded by the NIH. If something's been funded by the NIH, it can skip that step because it's already gone through scientific review. There's a CRU review to make sure that the clinical research unit can do everything that's proposed in the protocol, and an IRB overall review, which reviews many things, but primarily the general idea of the risks versus the benefits to the subject, and to make sure that the consent process is followed correctly, so people know exactly what they're getting into and what the risks are to them. And then there's also safety monitoring, because particularly for larger trials, but even for small ones, we need to be aware of whether or not what we're doing it has any potential risks to the patient that are being realized. And then there's post-approval monitoring, where there's auditing of whether or not you're following everything on your protocol appropriately. So just to tell you a little bit about our trial, so we recruited lots of people, so all of these inclusion and exclusion criteria were defined in our subject protocol. Basically, we were looking for males who had prediabetes, but were otherwise healthy and stable in weight, and that they weren't taking any weird medications or had other diseases that might affect their response to these diets. They also had to be willing to discontinue any supplements or weight loss products they were taking. And overall, the methodology here is that we pre-screen people. We recruited them in both by screening medical records and putting flyers around campus and the Madison area. We got at least one person from a library flyer, and placing advertisements in the Isthmus. And then if they were interested and possibly had prediabetes, they came in for screening. They also tested palatability of the various meal replacement products that we were having. And the subjects were randomized at visit 2 after they passed eligibility to either 2 meal replacement beverages per day of BCAD2 with 0 branched amino acids, or 2 meal replacement beverages per day of whey protein. And this could be made up in a variety of different flavors. And then from visits 2 to 4, the subjects eat a normal third meal and snacks as compared to their baseline intake. We do a lot of procedures there to measure basically parameters related to obesity, body composition, strength, and glucose tolerance. And so primarily this was a small trial to test the feasibility of our data. And our data overall suggests that we did meet our primary outcome, which was reducing branched amino acid intake by about 50%. And you can see here, overall protein intake didn't change very much, but we managed to decrease leucine, isoleucine, and valine consumption by an average of about 50% in our subjects. Whether or not this is sufficient for humans is not clear. So the average human probably eats about 4 times the RDA of branched-chain amino acids. So we should be able to cut that by about 75% or so without affecting their health. And here we've only cut it by 50%. And so we might want to be able to do that more in the future. Overall compliance was very good. The people who passed our palatability assay and were willing to take $1,000 for successfully completing the study didn't really miss any of the beverages and overall didn't eat too many additional meals. There were some adverse events. Basically, everybody reported some form of diarrhea or fecal urgency. Apparently, this is relatively common when you replace a lot of solids with a lot of liquids. And so that's something we need to think about going forwards. One of the things that did come up was the idea that if somebody has diarrhea multiple times, that's potentially a safety issue. And so we need to make sure that we follow appropriate safety protocols in reporting that to a physician that we had recruited as our independent safety monitor. And overall, people liked the beverages. And so they're willing to drink them. They found them tasty. In order to balance out the calories, they contain tons of sugar. So presumably they should be very tasty in that regard. So our conclusions from that study are that BCAD2 based meal replacement beverages are able to reduce branched-chain amino acid consumption in humans using this paradigm, and that the side effects, even though they're present, are tolerable and compliance is high. And so we're working on getting funding now to expand this to a fully powered study where we can get real data on metabolic outcomes to determine if this reducing branched-chain amino acids can improve metabolic health. So that is what I have to tell you today.
Thank you.
Thoughts, comments, questions?
I was actually just wondering, I feel like I should have asked you this before, but with the maple syrup RAM patients, do we see any metabolic differences? Like, has anyone actually studied or is like the like, because they have a natural deficiency in the ability to process BCAAs?
So the problem is that there's no untreated patients. Well, there's one problem is there's no untreated patients. The other is I really wanted to know how many branched-chain amino acids those people ate because I thought that would be a good amount to feed the subjects in our trial. But I talked to some of the nurses or nursing or RNs over at nurse practitioner. That's what I'm going for. Over at Wiseman, and so basically the problem is that everyone's individually titrated. And so someone who is a competitive swimmer actually eats more branched-chain amino acids than someone who has no disease and is sedentary. And so because they have very high demand in their muscle, and as long as it's being sucked up into muscle and incorporated to protein, everything is fine. The problem is if it's not, if they're eating too many branched-chain amino acids, it floats around in their blood and then bad things happen. And so I think overall the answer is it's not clear. Just to make things more confusing too, it turns out that many people who have maple syrup urine disease still process a percentage of the branched-chain amino acids. It's just a very low percentage because they have a mutation. But it might be interesting to look at. I think anyone who's really compliant is probably also, I would guess, is thin, but I don't know that. But it's hard to separate out because, and they're spending so much time thinking about their diet. Probably, what are they eating?
Right.
Yeah. Compliance is a problem because the powder doesn't taste that good, as you know.
Yeah.
Well, I don't know if you tasted it, but
The guy that we couldn't put through last week, so that Lisa just gave me all the drinks to try instead.
they're not that bad. But
it's not the worst thing.
Our first one said he really liked banana. He only had the banana ones. But
Yeah.
all right, thank you.